Hello there, and welcome to Introduction to Statistics Part 2, Comparative Statistics, using Excel, by me, Dr. Alan Brain. Now this is Part 2 of our Introduction to Statistics using Excel. This session we'll look into comparative statistics. So in this course we'll cover distributions, null hypothesis, t-test, and chi-square. So first of all, we'll jump straight into distributions. Whenever we look at statistics, we need to consider the distribution of the numbers. Majority of times, the distribution will be focused around the mean. This is called a normal distribution. So what is a normal distribution? A normal distribution is a continuous distribution that is bell-shaped, as seen in the picture on the slide. Okay, we don't always have a normal distribution. Sometimes we have a skewed distribution. Skewed distributions are not symmetric. Imagine stretching out one side of a bell curve. The stretched out side is considered skewed. So, a typical one is a distribution of wealth. We know that is not a normal distribution. And the two different types of skewed distributions are shown below: positive and negative. Null hypothesis. The null hypothesis states that there is no relationship between two measured occurrences. As a statistician, you need to disprove this hypothesis and discover a relationship. Examples of null hypothesis statements could be: there is no relationship between age and eyesight performance, and there is no relationship between waist size and height. The null hypothesis proposes the opposite we want to prove. The way we do this is by conducting tests to calculate the significance level, or P. As a general rule, if P is less than 0.05, which represents 5%, then we can say that there is a significant difference between the sets of data, and we can therefore reject the null hypothesis. P calculates the probability of the occurrence happening by chance. A common comparative statistical test is the t-test, which is used when the two sets of normally distributed data to compare. In Excel, we've got a simple formula where we put down t-test, range 1, range 2, tails, and type. This returns the p-value, not the t-statistic itself, which is not reported and we do not need. But as we can see now, we've got two new terms, tails and type. This is going to be discussed on the following slides. Tail tests depend on the distribution of the data. By choosing one side, you are only interested in one part of the distribution, either very lowest or very highest range of the numbers. For two-tail, we are interested in all the population distribution. Tails can be 1 for one-tail test or 2 for a two-tail test. But general as a rule of thumb, we would use a two-tail test, which tests for differences regardless of sign, negative or positive numbers. Now type. This is a very wordy slide. As before, I'm not going to read through all this, but you can press pause and read it at your own time. So now we'll dive straight into our t-test example. Suppose you want to moderate test effect of a prescriptive antidepressant drug. You ask a random set of people their well-being, score them 0 to 20, then about 10 of them you start giving them the drug. After a week, you ask the same people how they feel. So our questions will be: what is your null hypothesis? Calculate the mean and standard deviation. Calculate its t-test to see if the averages are significant. So what is our null hypothesis? Well, null hypothesis would be the drug does not affect people's well-being. So this is what we're going to try and disprove. So next stage is to calculate the mean and standard deviation. These are simple formulas done in Excel, which we did in the first course. Now we're going to calculate its t-test to see if the averages are significant. Now, as the range of effects can go up or down, this means that tails equals 2. And as we are testing the same group of people, the type equals 1. And we see the formula on this page here. And we can determine that the chance of this occurring by chance alone is 0.014 or 1.4%. So therefore we can reject the null hypothesis in favour of an alternative. Only once or twice 100 times, if we repeat the experiment, would we get a t-statistic of this aside. We therefore conclude there's more likely to be some systematic deliberate cause. If all other confounds are eliminated, this systematic cause must have been the drug. And a second example. You become a teacher. You've been approached by a medicinal company to try out a new drug that claims to enhance the intelligence of children. You split the class into two, with one group having the placebo, that's our group 2, and the other the drug, that's your group 1. You record the change in test scores as shown on the side. What is your null hypothesis? Use Excel to calculate the mean standard deviation and calculate its t-statistic. So what is our null hypothesis? The new drug has no effect on child scores. Again, this is what I want to try and disprove. Now we can use Excel to calculate the mean and standard deviation. Again, very simple formulas. Now we're going to calculate its t-statistic. As the range of x can go up or down, this means the tails type is 2. And then we are testing two different groups, type equals 3. So that explains our formula we need to put into Excel there. So on average, a child's intelligence increases by 15.2% points. The t-test provides a figure of 0.001, which means that these results are very significant and can only happen by chance 0.1% of the times. Therefore, we can reject the null. And now we are going to use chi-square statistics. The statistics so far have concerned measurement data. Sometimes the results are not measurements but counts, such as counts of species in different habitats. To compare frequency data in different categories with the expected data, you tend to use a chi-square test. This returns the probability p that the null hypothesis, which states that there is no difference between the observed and expected frequencies, is true. And as before, if p is less than 5%, then the data do not agree with the theory, and if p is greater than 5%, then the data agrees with the theory. So now we'll do a quick example of chi-square. We go for a walk in an ugly forest and comment on the number of apples. We expect to see 3/4 of red apples and 1/4 white apples. From 130 observations we noted 545 apples and 185 green apples. First, we need to calculate the expected. So, from 730, we expect 3/4 of that to be the red apples, which is 547, and then we expect the remaining to be green, which is 182. So we've now got our observed and our expected. Next stage is to calculate the chi-square statistic. As we see from here, it's just a simple chi-test, C3, C4, comma D3, D4. Very simple Excel command. And with p greater than 0.05, we can say that our theory was correct. We did observe 3/4 red and 1/4 green apples. And the reason why I use chi-square, not simple arithmetic, is to be certain that our results are significant and we can announce our results with confidence. That's the basics. We can now proceed to more exciting statistical work that follows. Additional material is available in these books and on the website. Thank you.